So now we're going to follow up our discussions in Chapter 9-1 with Section 9-2. In this particular section, we're going to do a hypothesis test for a population mean for a quantitative variable, and sigma is known in the population. Our objectives are to perform the hypothesis test with the p-value method. We're going to describe the relationship between hypothesis tests and confidence intervals. We're going to describe the relationship between alpha and the probability of error, and report the p-value or the test statistic value. Distinguish between statistical significance and practical significance. In our previous section, we discussed how to construct the hypothesis and write the conclusion for a hypothesis test. Now we're going to turn our attention to actually performing the test. There are two ways to perform the hypothesis test. Both methods produce the same results. The methods are the critical value method and the p-value method. In our class, we're only going to learn the p-value method. In a hypothesis test, the idea is to select a sample, calculate a statistic such as x bar, and compare it to the value in the null hypothesis h naught. If the difference between the sample mean and the value in h naught, that is mu, is large, it is less likely to be due to chance, and h naught is less likely to be true. Otherwise, a small difference may be due to chance, and h naught may well be true. We must determine how strong the disagreement is between the sample mean and h naught. We begin with an example. The College Board reported that the mean math SAT scores in 2009 was 515 with a standard deviation of 116. Results of an earlier study suggest that the coach students should have a mean score of approximately 530. A teacher who runs an online coaching program thinks that the students coached by his method have a higher mean score than this. Because the teacher believes that the mean score for his students is greater than 530, the null and alternative hypothesis are the following. Mu equals 530, which is the null hypothesis, the current condition, and h1, which is the alternative, is mu is greater than 530. Suppose now that the teacher draws a random sample of 100 students who are planning to take the SAT and enrolls them in the online coaching program. After completing the program, the sample mean SAT score is x bar is equal to 562. This is higher than the null hypothesis value of 530, but determine how strong the disagreement is between the sample mean and the null hypothesis mu equals 530. We calculate a value of the test statistic, which is just the z-score of the sample mean. Assume that the population standard deviation is 516. The test statistic is the sample mean, x bar. So we use the z-score, here it is, x bar minus mu naught divided by the standard error of 116 divided by the square root of 100. We get the final result of 276. And now visually we can see from the figure that our observed value, 562, is pretty far out from the mean value, mu, of 530. Intuitively, it appears that the evidence against h naught is fairly strong. So to see if the previous results and determine how strong they are, we're going to perform the same test with the p-value method. The p-value is the probability that a number drawn from the distribution of the sample means would be as extreme or more extreme than our observed value of x bar. Unlike the critical value, the p-value tells us exactly how unusual the test statistic is. For this reason, the p-value method is more often used in practice, especially in technology is used to conduct a hypothesis test. The smaller the p-value, the stronger the evidence against H naught. So our idea is we come back to this idea of the sampling distribution. And in fact, when we do have a normal distribution, we're looking at the difference between where mu naught is and where x bar falls under the sampling distribution. If this distance is very far, we're looking at the area that is to the right of x bar, especially if h1 is mu naught, mu greater than mu naught. So when mu naught is greater than mu naught, we're looking at this area. This area is called the p-value area. And we can also look at when h1 is less than mu naught on the other side of mu naught. And we can also look at the case where h1 is different, or mu naught is different than mu naught. Consider again the above example. An online coaching program is supposed to increase the mean SAT math scores to a value greater than 530. And again, our null hypothesis is mu equals 530 versus the alternative of mu greater than 530. Now assume that 100 students are randomly chosen to participate in the program and their sample mean score is x bar is equal to 562. Suppose that the population standard deviation is known to be 116. Does this provide strong evidence against the null hypothesis h naught mu equals 530? Recall that we begin by assuming that h naught is true. Therefore, we assume that the mean of x bar is mu equals 530. Since the sample size is large, we know that x bar is approximately normal, distributed with a standard deviation of 116 over the square root of 100. That is our standard error. The z-score for x bar is z is equal to x bar minus mu naught divided by the standard error. And when we do the calculation, we get the 276. So that's telling me we are 2.76 standard deviations away from the mean value. So because we look at the fact that h1 is mu is greater than 530, we're now looking at the area just to the right of 562. So the p-value is the area under the normal curve to the right of 2.76. This area under the table A2 equals 0.0029. Therefore, the p-value for this test is 0.0029. Such a small value of the p-value strongly suggests that h naught should be rejected. We have seen that the smaller p-value, the stronger evidence against h naught. Therefore, to make the decision to reject h naught when using the p-value method, we choose a significance level alpha between 0 and 1. You will recall that when we were doing the calculations for confidence level, the confidence level is equal to 1 minus alpha. Well, they're interrelated. So to compute the p-value, once we compute the p-value, if the p-value is less than alpha, we will reject h0. There is our rule. If the p-value is greater than alpha, we do not reject. So if p-value is less than alpha, we say that h0 is rejected at alpha level of significance, or that the result is statistically significant at alpha level. Suppose we found a p-value that was equal to 0.0122. The question is, do you reject h0 at alpha equal 0.05? Well, you'll check that in just a second. Do you reject it at 0.01 level? Well, the solution is, because the p-value is less than 0.05, right, we reject the null hypothesis at the 5% significance level, right? In part 2, B, because the p-value is greater than 0.01, we do not reject alpha at the 1% level of significance. So, the mean height of adults and men in the U.S. is 69.7 inches with a standard deviation of 3 inches. A sociologist believes that taller men may be more likely to be promoted to positions of leadership. So the mean height mu of male business executives may be greater than the mean height of the entire male population. A simple random sample of 100 male business executives has a mean height of 69.9 inches. Assume that the standard deviation of male executive heights is sigma equals 3 inches. Can we conclude that the male business executives are taller on the average than the general population at alpha is equal to the 5% significance level? First, we check the assumptions, and in this case, since n is greater than 30, the central limit theorem can be used for the sampling distribution. The null and alternative hypothesis are as follows. For h0, mu is equal to 69.7. That's our initial condition. And the alternative is h1 is mu is greater than 69.7. Because the assumptions are satisfied, x bar is approximately normal, with the mean of mu is equal to 69.7 and a standard error of 0.03. The test statistic is given by z, and z is equal to x bar minus mu naught divided by the standard error. When we put those values in, we get 0.67. Since this is a right-tailed test, the p-value is to the area of the right of z equal 0.67. So we use the table A2, or technology, and we find the area to the right of z, 0.67, to be 0.2514. The p-value of 0.2514 is not unusual, and since the p-value is greater than 5%, we do not reject h0 at the 5% significance level. There's not enough evidence to conclude that male executives have a greater mean height than adult males in general. The mean height of male executives may be the same as the mean height of adult males in general. So our second example is, at a large company, the attitudes of workers are generally measured with a standardized test score. The scores are on a test that range from 0 to 100, with the higher scores indicating greater satisfaction with their job. The mean score over all the company's employees was 74, with a standard deviation of sigma equals 8. Some time ago, the company adopted a policy of telecommuting. Under this policy, workers could spend 1 day a week working from home. After the policy had been in place for some time, a random sample of 80 workers was given the test to see whether their mean level of satisfaction had changed since the policy was put into effect. The mean was 76. Assume that the standard deviation is still sigma equals 8. Can we conclude that the mean level of satisfaction is different since the policy change at the alpha equals 5% significance level? Again, we check the assumptions. Since n is greater than 30, we can use the assumptions under the central limit theorem for the sampling distribution. The null and alternative hypothesis are as follows. We set up mu is equal to 74. Mu is not equal to 74. Because the assumptions are satisfied, x bar is normally distributed with a mean value mu is equal to 74 and a standard error of 0.8944. The test statistic is given by z is equal to x bar minus mu naught divided by the standard error. And when we do the calculation, we get 2.24 standard deviations from the mean. Since this is a two-tailed test, the p-value is the sum of the area to the right of z of 2.24 and to the left of negative 2.24. Because it's a two-tailed test, we must add those two areas on either side of the symmetric distribution. Using the table A2 or technology, we find the sum of these areas to be 0.0250. And since the p-value in this case is less than or equal to 5%, we reject alpha, we reject H naught at the alpha 5% significance level. So therefore, we conclude that the mean scores among employees has changed since the adoption of telecommuting. So we're going to use technology to find most of our z-tests and p-values. So the z-test command will perform a hypothesis test when the population standard deviation sigma is known. This command is accessed by pressing the stats and highlighting the test menu. So here is when we hit the stats key and we move over to test, we'll get this menu screen, and it's option 1. If the summary statistics are given, we use the stats key. We use the stats option to enter our information in. If the raw data of the sample are given, again we use the data option in the z-test. So again, we'll do the same type of example for the large company and attitude of workers that are regularly measured with a standardized test. Again, the scores range from 0 to 100. The higher scores indicate greater satisfaction with their job. The company's overall mean score was 74 with a standard deviation of 8. The company developed a policy of telecommuting. Under this policy, workers could spend 1 day a week working from home. After the policy had been in some place for some time, a random sample of 80 workers was given the test to see if their mean satisfaction level had changed. This new sample mean for scores was 76. We again still assume the population standard deviation of 8. we want to test the level of satisfaction at alpha equal 5%. Again, since n is greater than 30 and the population standard deviation is known, then the normality assumptions apply here. Now we press the stats key to do the test. We'll move over to the test. We'll pick option 1 and hit enter. Then we'll select stats because all we have is stats. We don't have the raw data. We'll enter in 74 for mu naught. We'll enter in for sigma. We'll enter in 8. For x bar, we'll enter in 76. And for n, we'll enter in 80. And because the alternative hypothesis is not equal to, we'll choose the first option, not equal to m naught. Then we'll hit calculate. When we hit calculate, we get a z-value of 2.236, such and such. And we also get a p-value. And the p-value here is automatically added for the low end and the upper end. So you don't have to do that calculation. And so since the p-value is 0.0253, it is less than 0.05 level of significance. So in this case, at the 5% significance level, we will reject the null hypothesis and conclude that the mean score for employees has changed since the adoption of telecommuting. So now we want to describe the relationship between hypothesis tests and confidence intervals. In the previous example, we rejected H naught mu equals 74 at the 5% significance level. In doing so, we are saying that 74 is not plausible value for mu. Another way to express the information about mu is through the confidence interval. If we construct a 95% confidence interval about mu, then the attitudes of workers we find in the interval to be 74.247 less than mu, which is less than 77.753. In other words, here's the lower bound of our confidence interval. Here's our upper bound of our confidence interval at 95%. Notice our confidence level, our C level, is equal to 1 minus alpha. In this case, since alpha is 5%, 1 minus 0.05 is equal to 95. So we have to calculate a 95% confidence level when we use alpha at a significance level 0.05. We also note in this particular case that this interval does not contain the null hypothesis value of 74. The confidence interval for mu contains all the plausible values for mu. Because 74 is not in the confidence interval, 74 is not a plausible value for mu at the 95% confidence level. So, in general, in our test statistics, if we do a hypothesis and we reject H naught, typically we do a confidence interval to reflect the new value for mu. Describe the relationship between alpha and the probability of error. You will recall that a type 1 error, if we reject H naught when it is true, is a type 2 error occurs if we do not reject H naught when it's false. We would like to make the probabilities of these errors small. The probability of the type 1 error is equal to the significance level, alpha. In other words, if we perform a test at a significance level 0.05, the probability of making a type 1 error is 0.05. Because alpha is the probability of a type 1 error, why don't we always choose a very small value for alpha? The reason is the smaller the value we choose for alpha, the larger the value beta, the probability of making a type 2 error. Report the p-value of the test statistic value. Sometimes people report only the test results that was statistically significant at a certain level without giving the p-value. It is much better to report a p-value along with the decision whether to reject. There are two reasons for this. There is a big difference between a p-value that is barely small enough to reject and one that is extremely small. For example, at alpha equals a 5% significance level, there is a huge difference between a p-value of 0.049 and a p-value of 0.0001. Not everybody may agree with your choice of level of significance alpha. By reporting the p-value, we let people decide for themselves at what level to reject H naught. So we want to distinguish between statistical significance and practical significance. When a result has a small p-value, we say that it is statistically significant. It is therefore tempting to think that a statistically significant result must always be important. Sometimes statistically significant results do not have any practical importance or practical significance. For example, in a new study, a program may raise student scores by 2 points on a 100-point scale. This improvement may have statistical significance, but is the improvement important enough to offset the cost of training teachers and the time investment on behalf of the students? So what you should know out of this section. What are the assumptions for performing a hypothesis test about mu when sigma is known? How to find and interpret a p-value? How to perform a hypothesis test about mu when sigma is known with a p-value method? How to describe the relationship between the hypothesis test and the confidence interval? How to describe the relationship between alpha and the probability of error? And how to distinguish between statistical significance and practical significance. And finally, why is it better to report a p-value or a test statistic along with the decision of a hypothesis test? Well, that concludes our chapter 9-2 on the test statistic or calculating a test statistic when we know sigma. Our next objective is to look at when we do not know sigma and how to calculate the test statistic. And that is in section 9-3.